what I want to do is present today the three different topics that have some relevance to the agronomic side of irrigation management. And starting with the first topic is infiltration. Let me see here. Okay. Well, I'm not. There it is. Okay, I'm sorry about. Okay. Well, infiltration. When we look at what affects crop yields, I came across these numbers here, and climate certainly drives our crop yields. When we add irrigation into that, climate has a little bit less of an effect, but there are a number of different things that affect our crop yield, soil being one of them, and I'm going to spend some time discussing the different ideas in soil and crop management. And welcome to the High Plains. We're in a very diverse environment. We can have, it can be too wet and too dry at the same time. Today we're seeing a lot of different things. These are some terminologies. When we start talking about salt water, we'll be addressing these things, these different descriptors, and what they mean. Just kind of boil it down. Term aggregate, granule, and crumb, little chunks of soil. Micropore, mesopore, and macropore. Talk about the holes that are in the soil, the holes between those chunks. We talk about infiltration and permeability. Those are things the soil does or happens in the soil. And then we talk about porosity, texture, aggregate stability, and bulk density. And I'll discuss some of these different terminologies and try to put them in perspective. But these are all different things that have to do, and you may run across it your further sessions with the irrigated program. When we talk about water holding capacity, and that's a real key property of the soil, two things govern that, texture and porosity. Well, first off, we'll talk about soil texture, and this is what we do in the lab. One of the things we do at Certec, we can determine soil texture it's called by hydrometer, and we identify the percentage sand, percent silt, percent clay, and then it's classified. This is a USDA soil textural triangle, and it describes the different types of soil texture, from clay to sand to silt loam to loam or whatever. And when we talk about the sand particles, we're talking about sand, silt, and clay. We're talking about particles that are of different size range. And we measure those particles in microns, which is 1 micron is about 1/25,000th of an inch. So anything 2 or smaller is a clay particle, 2 microns or smaller is a clay particle, 2 to 50 is a silt particle, 50 to 200 is a sand particle. Larger than that would be coarse sand, gravel, and that sort of thing. But that's what we're talking about when we talk about soil texture. This is some photographs through a microscope of clay particles. And there's different types of clay. They're different mineral types. And if you look at them, they're kind of flat and platy. And if I was in front of you here, one of my demonstrations is I hold in one hand, I hold a basketball, and I hold a playing card, like from a poker or canasta deck. And I came across an average fog droplet, so I want you to use your imagination, and I'm going to try to put the soil particle sizes in perspective. Imagination, and that basketball is the size of a fog droplet. You're walking in a foggy day, and there's those tiny, tiny droplets of moisture floating around. Well, that's about 5 microns across on average. Now, at the 5 micron range, that playing card would be about the size of a medium-sized clay particle in that size range I talked about earlier. Now, a mid-range silt particle at that scale would be equivalent to a stack of king-size mattresses about 6 feet tall. And a medium-sized sand particle, where you can kind of feel the grit, would be a boulder about a city block in diameter. So these are the size ranges we're talking about. And so it's helpful to me in going through this exercise of size comparison, and I'll use it some more just to help put things in perspective. Now, when we talk about soil aggregates and pore spaces, we're talking about those chunks of soil. And we've got sand and silt and clay particles kind of bound together with organic matter. They're kind of stuck together to form the granules. And we talk about a soil having good tilt. You pick it up and it breaks up into these nice little crumbs, an eighth of an inch or so in diameter. Well, that's what we mean when we talk about soil aggregates. And pore spaces, we're talking about the spaces between those granules and also between the individual particles within that soil aggregate. And so these are things that drive water holding capacity. So one of the important things to remember is that as we get smaller and smaller particles, we get more and more surface area. And I ran across this reference. If we take 1 gram of soil, which is about a heaping half teaspoon of soil, the surface area of a coarse sand on all those different particles is about 1.5 inches square. And as we go to the finer and finer particles, it gets more and more surface area. And if we had pure clay, we would have nearly 1/5 of an acre in that 1 gram of soil, 1/5 of an acre of surface area. And this is important because one of the characteristics is water will kind of wrap around in films around that surface area, depending on how it is, but it sort of wraps around these particles. So we have more surface area in that soil. We simply have the ability to hold more and more and more water. So as we start talking about how much water that soil can hold, here's a diagram to illustrate. And there's a terminology. We use saturated soil, field capacity, skip over allowable depletion for a minute, permanent wilting point, and oven dry. And over the right is what the characteristic would be in terms of soil water. So if we took an oven dry soil, took it and cooked all the moisture out of it, and started adding water to it, eventually we would see the soil would become saturated. All of the pore spaces, everything would be filled with water. And that's a point where we have saturated soil, we start to get runoff, we start to get waterlogging in low areas. Now if we took a bucket of soil, say, and we wet it up to saturation, we let it sit for a day or so, it would drain, the excess moisture would drain out until about 1/3 or so of those pore spaces would have air in them. The rest would have water in them. Well, that's what we call field capacity. As that soil dries out and gets drier and drier and drier, now that's water that plants can use. But eventually we hit a point where the plants simply cannot extract any more water from the soil. And that's what we call our permanent wilting point. So we can still have water in the soil, but it is unavailable to the plants. A good example would be, think about taking a sponge, soaking it in water, and setting it on a table. Well, the water would drain out, it'd be waterlogged, it would drain out, and once the excess water drained out, that was what we would call field capacity. Now you could take it and squeeze water out of it. And you continue squeezing harder and harder, and you squeeze more and more water. But eventually you get to a point where no matter how hard you squeeze, there's still water in that sponge. And that's what we're talking. Instead of squeezing, it's the plants are extracting water from that. So when we talk about irrigation management, we try to take a look at the available water capacity of the soil, but we try to manage it in a certain way so we only deplete about half of that available water. If we start depleting past that, we start cutting into yield. So irrigation management, we're trying to maintain for good crop production that range and readily available water capacity. So that gets into scheduling and all these sorts of things, but that's the terminology that we're talking about here. Now when we talk about pore spaces, I was talking about the holes in the soil, I'm using pipe sizes, and this is at that the clay is equivalent to a clay particle equivalent to a playing card at that scale. So if we look at the equivalent sizes there, our water stored in pipes that are 0.1 to 30 microns, they're over the right hand side, but equivalent to 1 to 5 feet, 5 foot in diameter pipes. Anything larger than that, the water kind of flows through and drains out of the soil. So we're talking about available water being in those pipes, in those holes, if you might think, that are the equivalent of 10 inches to 5 feet in diameter sizes. So it's really, if it gets the water in the smaller pipes or the smaller pores, is simply unavailable. It's held so tightly that the plant simply can't extract it. So again, we try to manage the available water in that when we're dealing with irrigation management. So as we look at soil, as we go from sands to higher and higher clay, we have more clay, we have more surface area, so we have the potential for holding more water. But the problem then is that clay particles also, they hold more water, but they hold it more and more tightly than sand and silt particles. So if we have a sandy soil, we can hold a total of about 1 1/4 inch or so of water before we start draining, before it starts moving out. We go into a clay soil, we can hold close to 4.5 to 5 inches of total water before we start reaching saturation. But even though we hold almost 5 inches of total water, still we've got about half of that or so is considered available water. Some of it is held so tightly, about 2.5 inches is held so tightly that the plants can't extract it. So we need to know about soil texture. The clay content gives us some information about our soil water holding capacity. Now, when we talk about infiltration, the two characteristics that affect it are what we call the texture and the porosity. So water infiltration, that's just water moving into the soil. And it's affected by all these different things: the texture, sand, silt, or clay content. How wet was the soil before we start? Do we have surface sealing, or do we have good structure? Do we have good granulation, good till? Are there cracks in the soil? How we till, what we do with it, will affect that infiltration. And then our application method. Furrow, we have overhead sprinklers, low angle impacts, those sorts of things. All have an impact, will affect the water infiltration. So as we look at water infiltration, this is a chart I ran across, just shows typical minimal surface sealing under good infiltration conditions, from clay loam to coarse sand. So we can move a lot of water as it gets sandier and sandier and sandier. But if we start having some surface sealing for whatever reason, a little compaction, raindrop impact or droplet impact, which will break up some of those soil, break up those aggregates, break up those granules and start it sealing off, we can drop that infiltration rate kind of pretty dramatically. So good management, overall management, is going to have an effect on water infiltration rates. Now, if we look at over time, as we start adding the water to the soil, if we start out with a bone dry soil and we start adding water to it, the first few inches, time here of that we start adding water, we have a pretty high infiltration rate. But that infiltration rate drops off fairly rapidly as that water starts to get saturated. And eventually we reach a point where we have kind of a steady state, where that infiltration rate, and I'm talking about what we observe at the surface of the soil, that infiltration rate levels out. And that infiltration rate, as we increase the clay content, going from fine sand to silt loam, that total infiltration rate drops off. But it follows a real similar pattern. So we have rapid infiltration early on, and it drops off after a period of time, depending on the soil texture and some other things. Now, if we look at not just the surface, but we start looking below the surface, how fast does it move through the soil profile? We flip that over. We see very rapid, deep infiltration with the sands. We can move water very, very quickly, so to speak, through the profile. As the clay content increases, we it starts to drop off. And as these pore spaces get smaller and smaller and smaller, that drops off as well. So the surface infiltration and the depth of infiltration is affected by soil texture. It's affected by soil porosity, or the size of the pore spaces. This is just an example I ran across, this diagram that illustrated a sandy soil and a clayey soil, and this would be under a furrow irrigation system. So we run water at this point, and we can see here at 24 hours, just by comparison, the clayey soil had a lower depth, or less depth of water infiltration, but there was a lot more lateral infiltration than did the sand. The sand infiltrated very rapidly, but we didn't get much lateral infiltration. So that becomes an important consideration, the soil texture and the depth of our infiltration, and with, you might say, the lateral infiltration. These are all going to have an effect. So here's an example, just kind of a simple diagram of if we're looking at infiltration rate and irrigation application rate using a center pivot. So what this is showing is if we set a rain gauge here, and whatever time it was, when that sprinkler first hit the rain gauge, we'd see the rain gauge fill up, it'd reach about halfway point, and then over time the rate would drop off. So by the time we're done, we put on our, whatever it is, inch or whatever it is of irrigation. But it's over this time. But if we look at the infiltration rate compared to the application rate, what we'd have is we'd have that fairly rapid infiltration initially until that soil became somewhat saturated. And then that infiltration rate would drop off and reach that steady state. So this point is going to depend on a lot of different things. Soil texture, application, how much we're applying, how fast we're applying. And once we start getting this dropping off, that's where we start seeing our potential runoff. Initially, we might see surf ponding there on the surface. We're going to start to get some runoff and water loss. And so that's going to affect our irrigation efficiency. Now, when we look at water movement through the soil, this is there's a couple of names of a couple of YouTube videos that are kind of interesting. They're interesting, boring, I'm not sure, but they tell a lot about water infiltration and patterns of movement. And what they've done in these videos, and this is a good example, they took 2 sheets of glass, they filled it with soil, a narrow sheet of glass, and they put a drop of vegetable dye, and then they added water at the top. And so in this case, they added water at the top, and it's pushed that vegetable dye, so we can see the patterns of water movement through that vegetable dye. And if we go back to, people, if you still have or had furrow irrigation, we not only get vertical movement, but we get lateral movement. And so one of the things, if you've been around furrow irrigation, by the end of the season, sometimes you'll see kind of a surface crust build up here, some lime or some minerals build up. That's because the water has pushed soil minerals up to the top of that furrow, and they've been lost by evaporation. Also, how we till and where the residue is at has an impact. And what we're seeing here is if we have channels for that water to move through the soil, we can enhance the water movement. But if we have our residue, for example, in the old days of plowing, if you plowed and turned over the residue on the top and you built up a mat of residue below the surface, that can actually stop the movement and keep the water from moving into the subsoil. So tillage and management have a significant impact on water infiltration. So when we talk about tillage management, here's how that affects infiltration. First off, it affects the soil pores. The size, are they large, are they small, and the distribution. We have a lot of fine pores, we have a lot of coarse pores. That's affected. It affects the soil strength, so that's what it takes for roots to penetrate the soil and water to move through the soil. And some tillage we can compact soil, sometimes severely, or we may loosen soil. We can do one of those two things. It affects the distribution of the residue, how it's distributed over the soil surface. That's going to affect soil temperature, which doesn't necessarily affect infiltration. It would affect crop growth. It's going to affect moisture retention, limit evaporation, and it potentially affects the water movement in the surface and in the profile. This is a study I ran across that it compared conventional tillage to no-till, and looking at the long-term, the pore size comparison. So the dark brown bar is the conventional, I'm assuming, plowing, chiseling, working it. The light brown bar is no-till. And here are some poor grad student had to go and figure out these different pore sizes by microns, and I've done the calculations here back to our pipe sizes to do some comparison. So as we look up here at unavailable water, if we go back to our diagrams here, this is the pore size where we have unavailable water. Our readily available water is in this pore size, and then our drainage is this size of pore space. So as we look at no-till, we tend to have, comparatively speaking, more finer, smaller pore size, finer pore sizes. And so no-till will retain more moisture, but it will drain a bit. If we look here at conventional tillage, we've got more of the larger pores, so we can actually, we chop up the soil and we create some pathways. We get better internal drainage, at least for a period of time, with conventional tillage compared to no-till. Now, another important to think about is the impact of rooting on water infiltration. As we look, these are some photographs taken through a microscope. Here's a canola root on this side, and wheat root on this side. And what I've done is done the equivalent of the microns, taking those microscopic measurements and convert it back to our scale using the playing card that's clay size. Now, when you look at a root system, you dig up a plant root, and let's take this wheat root for example. The white root you see doesn't really take up much water. It's the root hairs, the fine fuzz that would grow microscopic, that would grow out of that root is actually, this is what absorbs water and this is what absorbs nutrients. And just using that playing card example, a root hair would be like a 2-foot diameter pool floating that's, 50 to 150 feet in length. The same thing, you see this fine hairs here. That's the hairs that's the root part of the root system that extracts moisture and extracts nutrients. So what's the impact of those things? Well, this is, I ran across this phrase, soil management is the husbandry of holes. So what we're trying to do is manage the holes in the soil. And the reason we manage those holes is we want water to penetrate, infiltrate into the soil. We also want to provide channels for root systems to grow. If we don't have pore spaces, those root systems have a much more difficult time in developing. And what I'm showing you here is the results of, for about 15 years or so, I was doing some a project south of Dodge City in some fairly silt loam soils. We were probing down to 20, 30, 50 feet deep. And these are soil cores. Now, we used a 2-inch coring tube. So this core here is about 2 inches across. And I've circled, if you can see these little dark spots in here, little pinholes, here, 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 here. Those, I believe, are rivet channels, are rooting channels from old crop roots. The thing is that what you're looking at here are cores that were taken 30, 40, 50 feet deep. And my belief is that these are old prairie grass roots. We have a prairie growing for hundreds of years. And we look at our fires right now, we burn off the top growth, but the crown still remains. We don't kill that grass off, we just get rid of the top growth. So we go to the East Coast, we have trees that are 200, 300 years old. Why wouldn't we have grass plants that potentially could be 200 or 300 years old? And over that time, push their roots down and penetrate down to 30 and 50 feet. So that's my speculation, my opinion, but I found it very interesting. And so we find these certainly in the surface, but we can find these at depth. Well, here's what those root channels, the impact they can have. And here's an example on the left. Somehow they dissected, and you can see that root channel. So there's an old root that grew through there, and it died, and it left this channel behind. And what they've done is they've added water with blue vegetable dye, and you're seeing that water move down, and then it moved laterally. And so we can move water a bit faster through the soil. We tend to think of water moving sort of fairly uniformly from top to bottom, but it doesn't. It moves in sort of an erratic fashion depending on how we manage it. This was from that project where I took the deep profiles, and this was the Kansas Geologic Survey came out and did a study. What they did here was they built a little berm here with 2x12s and polytar, and they added water to it. They had a tank full of water. They added blue vegetable dye, and they put the equivalent of about 20 or 22 inches of water, like a full irrigation season, into that basin. They let it soak through, and then they came back with a backhoe and dug it. And what we're looking at is the side of that pit. And this here is a Harney silt loam, very productive. It's Kansas State soil, good silt loam soil, very productive. But if we look here, we got a lot, and this came from a field I might mention. It's probably been irrigated for a good 25 years. Mostly corn, might have had one or maybe two rotations of alfalfa in it, but mostly corn. What we're seeing here is down here to about 1.5 feet, we see a lot of root movement because we see all this dye, and this is called finger flow. Water flowed down and then flowed laterally. Well, this here down to 3 feet is it tends to have a higher clay content, and so we still see root movement through there. There's very faint blue streaks, but once we get past that, we're into a soil texture that has less clay content, and so those roots could expand and grow in the root system. So what we see on the surface and what's happening below the surface sometimes are not necessarily two different things, but can provide some head scratching. This over here is from an adjacent field that had been, they put a pivot up on it maybe 3 years before, just very shortly. Prior to that time, the farmer that had it, you might say he had a wheat with a bindweed cover crop. And when they dug this up, the speculation is this was from a bindweed plant. And this is this is called funnel flow. So it's really important. We think of water moving uniformly through these soil profiles. What here, if we think of this as a funnel, all the water in that top, 4 or 5 feet diameter circle, by the time we get down to 5 feet, it's concentrated down to maybe 2 or 3, a tube, if you will, 2 or 3 inches across. So as it concentrates here, it's going to move faster and faster and faster through the profile. So sometimes our profile water movement can surprise us because of these it's called preferential flow pathways, and it can cause some head scratching. Now I ran across this, when you're talking about infiltration, this headline, this has been 5-6 years ago in Nebraska, there was a bunch of flooding. And so this headline here, let this soak in, roots can reduce flood impact. And the implication was that maybe if we got living roots in the soil and got roots, that we would be able to control flooding. We could move water through the profile and limit the amount of flooding. You had to read into the article a little bit and find out that actually what they were talking about the flooding impact was simply loss of soil, loss of erosion. But you have to be a little careful, and want to go into this about what you read, what the headline, and what's behind the story. So this is an example. This fellow, Gabe Brown, he's kind of a guru of soil health, and this was a statement he made. He was talking about his water infiltration went from ½ inch per hour to 8 inches per hour. So that's fairly impressive over 20 years. And it's because he said because of his management system and some things he's done. Well, apparently I don't know if I believe this was done on, may have been done on his ranch, but this was a study by the USDA. And they were looking at some different crop rotations. And they were able to go from, depending on the crop rotation, from inches per hour, from 3 inches per hour to 11 inches per hour. That's really impressive. I mean, that was really surprising that a rotation could do that. But we were looking at different crops, different rooting systems, different patterns. Well, going back to another statement Mr. Brown made, right here he talks hand in hand, he has high organic matter levels, so he had good structure, good soil aggregates, some good pore space. An infiltration test done by scientists, and I think this is probably where the previous slide came from, said water infiltrates our soil at the rate of 1 inch in 9 seconds, and the second water in 16 seconds. That is pretty amazing. But I went and I took a look a little bit, and I did the math. If you take that and take it for so much 9 and 16 inches per second, or and moved extrapolated it out to feet per hour, we're talking about 20 to 30 feet of infiltration per hour, water moving through that. Well, if that was the case, you could drain. You could start at breakfast, and you could have Lake Meredith drained by supper time. So that didn't make a lot of sense to me. So I tried to look a little bit deeper. And I worked for a USDA when I was in college. I was the grunt labor. I worked for a USDA research group, and one of the things they looked at was infiltration. They were studying tillage systems, and this is what's called a double ring infiltrometer. You pound these rings in the soil, fill it with water, and then you measure the rate of water. This is a different type of instrument, but you measure the rate that the water drops in that, and you then can calculate your infiltration rate. Well, there's a simple way to do it. This is using a coffee can or a piece of irrigation pipe. You pound it in the soil, you add a certain amount of water, and you watch, use your stopwatch, and watch when that water drains away. And when I started reading this article and going back, I think that's pretty much what they did. They were measuring the infiltration rate in a 3-inch depth. So to a 3-inch depth, we went from 3 to 11 inches per hour in that 3-inch depth. Well, that gets back to our infiltration rate. This was a study that was done on a soil. The clay loam is real similar to, I think, Pullman clay loam. And what they did was they measured the infiltration rate per hour over 2-hour time period. So the first minute infiltration rate was almost 25 inches per hour, but after 5 minutes it was down to something like 7 or 8 inches per hour. 10 minutes we were down to about 6 inches per hour. 20 minutes or 5 inches per hour. 30 minutes we're at about 3 or 4 inches. And after 60 minutes we're at that steady state, so we're down to about 3 inches per hour. So very quickly, in those first few seconds, we can have a very, very high infiltration rate. But it slows down, and here's why. This is that same soil that I just showed you, but they were looking at a depth down to 3 feet. And so what they were seeing is over time, and these were wheat, and it was in an orchard somewhere, and they measured this. Well, anyway, they looked at the trees, where they had wheat roots growing. So you had roots in there, you had good infiltration, but it was a clay loam soil. Anyway, we started very, very quickly. We got a high infiltration rate, but as we got to depth, so once we got that first 3 inches of moisture in there, the infiltration rate slowed down because we had to push And once we saturated this top 3 inches, that water had to sort of be pushed down into the next 3 inches to make room for the some more water. And then that had to be pushed down further and further and further and further. So our infiltration rate initially in the surface was very rapid, but as we moved with depth, infiltration rate, that's what they measured at the soil surface. So as we moved down from 3 inches down to 3 feet, that infiltration rate that we measured at the surface got slower and slower and slower. And so that's an important consideration, not just what we see on the surface, but what we see through the soil profile. And we have to keep that, and I guess, keep that in mind, because, and I'm not there, but I'm assuming you've got someone out in the foyer with nozzle, different types of nozzles. And so when we're looking at irrigation, a lot of the engineering goes into the ability to maintain some kind of an infiltration rate so we can get good water penetration. Well, that is going to depend on porosity, that's going to depend on texture, that's going to depend on all kinds of aspects of our soil management. So just kind of to summarize here, when we look at texture, we're talking about a range of particle sizes: sand, silt, and clay. And it's important to remember not only the surface texture, that top few inches, but also the subsoil texture, because that's going to have an impact on total infiltration. If we've got sand at depth, it's going to move a lot more rapidly than if we have loam or clay at depth. When we talk about porosity, you hear that terminology. We're talking about pore spaces, holes in the soil. And when we talk about soil aggregation, that's the granulation. And so the presence of soil compaction or the lack of soil compaction is going to have an impact on the infiltration rate, as well as the degree of soil aggregates. Our root channels may have an impact on that. If we can maintain those root channels, well, we can get preferential flow and we can get water moving through the first few inches of soil, and it help improve that surface infiltration rate. But finally, we have to think about rainfall and irrigation. It's not what shows up in the rain gauge as what reaches the soil, but very importantly, the inflow rate per unit of time. And that's what we try to manage by, with irrigation speed and nozzle technology and that sort of thing. And then finally, one of the things that has an impact is water quality. And that'll be the next take a break here for me to move into the next topic. Okay, back. Proceed here with part 2. When we talk about water quality, that's an important consideration, and it's becoming more and more of an issue as our time that we've irrigated, as we've gone from 10 years of irrigation, 20, 30, 50, however many years of irrigation. And one of the things that we worry about a lot certainly is the volume, irrigation volume. We live in the High Plains aquifer, and it's being depleted, and so we're seeing areas where in the not so distant future we potentially going to run out of water. But its volume is important, but also the quality of that water becomes important. And I want to spend some time talking about that. And Forrest Gump here, irrigation water quality is like a box of chocolates. You never know what you're going to get. There's a lot of different things that affect water quality, and I'll talk about some of the aspects of that and what's going on. So when you get a water test report, whether it's from Surtec or someone else, you're going to see these terminologies, and you'll hear milligrams per liter, and that's just a way of expressing parts per million on a liquid basis. In some cases, you'll see a percent of something, and keep in mind that 1% is equivalent to 10,000 milligrams per liter, 10,000 parts per million. You may see a term micrograms, that's that little U shape, micrograms per liter. Sorry about that. And that's, we're referring to parts per billion. When we look at irrigation water analysis, we talk about ions, and ions are simply charged molecules or atoms. Some have a positive charge, some have a negative charge. The positive charge ions we call cations, and we're most concerned about sodium, calcium, magnesium, and potassium. The anions have a negative charge, and we're concerned about chloride, sulfate, bicarbonate, and nitrate. Now we talk about salts, and a salt is simply an anion, a negatively charged particle, plus a cation, positively charged. And when you talk about salts, and this is kind of scientific, but it's a crystalline substance, and it originates under natural conditions from weathering of soil minerals or rocks. Well, a salt, just a rough definition, is something that can dissolve in water. And we talk about ionizing in water, okay? Going from a crystalline structure to an ion. So if we have a table salt crystal, this is what it would look like if we could, it's in sodium and chloride atoms that are in a regular pattern, crystalline pattern. And once we put them in water, they break apart, they ionize. And so now instead of having a salt crystal, now we have chloride ions and sodium ions sort of floating around in the water. They're dissolved in the water. And so this is real important. Now, if we dry that, take that water solution and dry it back out, then we're back to crystallines and redissolve and back and forth and back and forth. And when we talk about salts, again, these are common salts: potassium nitrate, sodium bicarbonate, baking soda, magnesium chloride, Epsom salts, calcium sulfate, gypsum. These are all salts because they have an anion and they have a cation. They can be, they have different solubilities, but they dissolve in water and can ionize into the individual atoms. Now, as we look at these salts, our common salts, when we're talking about irrigation water, typically the chlorides are more soluble than the sulfates, and the sulfates are more soluble than the carbonates. So depending on the water characteristics and whatever, when that water dries out, when the water's evaporated off, we may crystallize out any of these different salts. But to redissolve, these carbonates are very hard, they're less soluble, so they don't redissolve, but the chloride salts redissolve very, very readily. Now, salts, there's two sides to the coin. First off, salts, and what we'll talk about is being potentially harmful. There's two things that salts affect. They have an effect on the crop growth, and it has to do with the total dissolved salt load, or how many ions are in the water. In some cases, we have an excess of certain ions like chloride and boron, and we can have toxicity from that. The second effect is the soil structure effect. Going back to the first section, the type of dissolved salts have an impact, and
Fred,
we are especially concerned about, yes?
Are you going through, the slides are stuck on the summary slide.
Oh my, okay, whoops. Wow, okay. Well, let me try this again. I apologize. Go through quickly. I'll try to, okay, let me screen share. Let me close that one out. Okay, we're back again. Okay. No, that's not what I want. Okay, here we go. Let's try this. Water quality showing up?
Yes.
Okay, all right. Again, I apologize for this. Let me get to this. Okay, buzz through real quickly. Volume versus quality. That's what I was talking about. Irrigation water. You don't know what you're going to get. And laboratory reports, milligrams per liter, parts per million percent is 10,000 milligrams per liter. Micrograms is parts per billion. Here's where we talk about our cations, positively charged cations, sodium, calcium, magnesium, and potassium. Anions, negatively charged chloride, sulfate, bicarb, and nitrate. And here's what I was talking about, the salt crystal, going from a crystalline form with our molecules, and we dissolve in water, and we ionize, so it breaks up into the individual molecules. And these are the common salts I was talking about. Baking soda, Epsom salts, gypsum. And solubilities, we go from chloride, most soluble, to carbonates, least soluble. When we try to redissolve, these are going to be hard to dissolve, and these aren't. Potentially harmful effect, the effect on crop growth, not only the total salt load, but the kind of salt that's in there can have an impact. And there's an effect on the soil structure. It's a type of dissolved salt, primarily sodium in the salt. Potassium may have an effect, and I'll take a look at that later. But there's also the other effect is they may be beneficial. These are nutrients. And if we look in our High Plains groundwater, sometimes we have nitrate, hopefully not a lot. We can find potassium, sulfur, magnesium, boron, and bicarbonate or lime. And these are fertilizer nutrients and can be used as that. Now, when we look at irrigation water, one of the things we want to look at is the effect of total salinity. And we measure dissolved salts. It's a total ion content. And you'll see a description in a lab report, electrical conductivity, soluble salts, specific conductance. And we use a conductivity. We don't measure the salts directly. But what we do is we have an instrument that we pass an electric current through a water sample. And if there's distilled water, we'll not pass a current. But if we start adding salt to it and start getting more ions, the more and more ions we have there, the more and more current passes between those electrodes. So more and more ions means a higher and higher salt content. And the example I use is if you are sitting in a bathtub and your spouse comes in and says, I've just taken out $1 million life insurance policy on you, and plugs in a hairdryer and throws it into the tub, you're probably all right. If it's distilled water, we don't have ions in there, so there's no way to pass the current. However, if the spouse comes in and says, got my $1 million life insurance policy, throws a handful of salt in, and then throws the hairdryer in, probably going to collect, because now we have ions. So the measurement units, you see a couple of different things. You see, we use micromoles per centimeter, or millimoles per centimeter. And micromoles, 1,000 micromoles is equivalent to about 150 pounds of salt per acre inch of water. So you can use that as kind of a guideline. So as our conductivity increases, that total salt load increases and increases and it may reach a point where it's a problem. And when we talk about saline soils, we're talking about excessive total salts. And keep in mind that the irrigation water does become the soil water. So any salts, any ions that are in that irrigation water, once that water is applied to the soil and we evaporate off the fresh water, well, we leave those salts behind. So over time, we can accumulate salts in the soil. And we talk about the osmotic effect on plants, and that's important. Osmosis is the ability of liquid or ions to pass through a membrane. And what we're talking about here is the ability of water, the membrane, the skin, if you will, of the root system of the plants. And what can happen is if the soil water has a higher salt content than the interior of the plant roots, fresh water is going to move from the lower salt content of the plant roots out into the soil water. The example here is just if you've ever made brine pickles. You take this nice crisp green cucumber and you put it in a vat, a crock with brine solution in it, and you come back, I don't know, a month, 6 weeks later, whatever, and you pull that same cucumber out, it's not fresh and green anymore. It's kind of light green and then shriveled up. Well, what's happened is the water has moved from the interior of that cucumber. It has a lower salt content, and so it's moved out and basically trying to dilute the brine in the crop. And that is not only the cucumber itself, but that's also the spoilage, the fungi and whatever else would cause spoilage. And so that's why we use salt to preserve things. We create an environment that has a higher salt content than the spoilage organisms. So what we can see here, and this is an example of a couple different wheat varieties that you get this water stress, and we talk about desiccation, drying out, and we can get dry moisture, because what can happen is you can get soil that feels wet, but because the salt content is so high, the plants are actually under drought stress. And it depends on the varieties and some different things. Now, when we look at how plants respond to increasing salt load in the soil, this is a picture of kale, and I can't think of a better thing to do than to kill kale, destroy it. But anyway, we see this initially, there's not much in effect, and then there's a drop off of growth or yield. And we talk about a threshold level, and then after we hit that threshold level, there's a certain percentage yield loss for every unit of increase in soil salinity. And it may be very fast, it may be very slow, it may be very high, it may be very low. But just to give you an example here, I ran across these experiments where we'll take a look at grain yield here. And this was a comparison of wheat and sorghum. So what we're seeing is the percentage of the yield, where we had 100% or 50% or 0% of yield, with increasing soil salinity. So as we look at sorghum, we reached our threshold point here, and we got a certain drop off. Wheat, we had a threshold point that was a little bit higher, but the decline in yield with increasing salinity was less and less. So different plant species may react differently to salinity. We have salt tolerant. Barley, for example, is extremely salt tolerant. There's some things that are very salt sensitive. And so we can manage salinity sometimes by picking and choosing the crops we use. Now there's also, when we look at, this was comparing grain yield, now we've compared vegetative growth or forage yield. So it's the same wheat variety, so we have a threshold that's a little lower and a decline. So we still have our wheat is still a pretty good crop here, and we've got two different sorghum varieties. We've got one that responds very much like wheat in terms of forage yield, and we've got one that has a lower threshold and a more rapid decline. So if there are salt sensitive varieties, and I know seed companies and stuff have picked out lines that are more tolerant, and so we can switch. Not only we maybe switch from a crop, a certain type of crop, but we may be able to pick varieties within that crop. So these are important. So different plants react differently. The salinity may affect growth, vegetative growth, and final grain yield differently. And different varieties within a crop species may react differently to salinity. Now, field conditions have a big impact, and the top graph is trying to show the impact of salinity on germination and emergence. So we have percentage of emergence in days here, a 2-week period. So we have low salinity. After about 3 days, we get full emergence, and we're done. As that salinity increased, that emergence is delayed, and we still reach 100%. It's delayed even further, and we eventually reach 100 final emergence. But if there's a certain point where our emergence is limited, and our emergence just doesn't happen. The soil condition, the soil moisture content has a big impact, and that's what this second, that's what this second diagram is showing. We're going from field cook. See, remember, we've got a full program all the way to permanent wilting point. So as we have low salinity, eventually we reach a point where that emergence drops off. As the salinity increases, we start to see that emergence drop off more rapidly and more rapidly. And eventually reach a point where we have very little emergence. And this is not only soil salinity, but also keep in mind when we talk about starter fertilizer management, and we talk about putting a certain amount of nutrients, a certain amount of fertilizer in the furrow or next to the furrow, a 2x2 or whatever placement. And we have certain what we call salt limits on there. Well, those fertilizer nutrients are salts. If they don't dissolve in water, the plants don't eat their food, they drink it. So those fertilizer nutrients, those fertilizer materials have to dissolve. Well, they raise the conductivity, they raise the salt level of the soil water in that band or that area that they're growing. And so, very same thing happens. We can get by with a certain level of nutrients, but as we increase the salinity, increase the salt load by increasing the rate of starter fertilizer use, we potentially delay emergence, and we may reach a point where we delay, we really damage emergence. Same thing is true with our soil moisture. When we have good spring conditions, we have decent soil moisture, what we see is just like this. We see where with low salinity, it dries out and we start having problems. But as we add up the rate of starter fertilizer, we start seeing slower and slower emergence and eventually reach a point. So as the soil is drier, we have more problems with the same rate of starter fertilizer. The last slide kind of concluded total salt load. Now, type of salt. We do run into situations and with chloride and boron. If chloride is applied to the leaves, sometimes the high chloride water, we can get this burning and such. The droplets, actually the chloride moves from the droplets into the leaf tissue, and if it accumulates past a certain point, you can start to have things like this showing up. The edges of the leaves burn, and we've seen situations where we defoliated soybean and edible bean crops with high chlorides. Now, boron is not so much of a concern. Some areas it is, but it enters into the soil and it's another toxicity. It builds up in the soil to excess levels. We can have toxicity. And again, our irrigation waters carry a certain level of this. It may or may not be critical or not. Now, I want to spend a little time talking about the effect of sodium on the soil. And when we see a sodium-affected soil, now we're talking about types of salts. One of the things we're looking at is the sodium versus the calcium, magnesium in the irrigation water and in the soil. And if we have excess sodium, what happens is the soil aggregates or granules depopulate or break down. We start to see crusting or sealing. You start to get runoff. You don't get water moving in the soil. You can't get air. The roots do require air. In fact, it gets to the point where we have what we call a massive soil structure because the aggregates and the granules are broken down. That's what we see here. This is a situation, extremely high salt content or sodium content, and I dropped the shovel in there and I popped up. It looked like a brick or cement block when it came up. And that was the soil that was field planted with soybeans. You can see what happened to the stand. So it can become a real problem. Now we have some measurements that we use to help us predict and get some ideas of the impact of the sodium compared to the calcium magnesium. Now I mentioned, I guess to backtrack just a touch, sodium causes things to disperse. And the example I use, a good example, is, I'm not sure if you've got coffee there. If you ever see coffee creamers, it's not really cream. But if you take, any of you raise calves or baby pigs or whatever, you use a milk replacer. And if you aren't careful, when you mix a milk replacer, you don't have milk, you have dough balls and white water. Now you think about coffee cream, you open that packet of coffee cream and you drop it into the coffee and it kind of blossoms out. And it really mixes well. it's different. Well, if you look carefully on the packet, many times you'll see a sodium silico aluminate. Sodium silico aluminate. That's actually bentonite clay. And bentonite clay is a high sodium clay. And we use it for sealing. And so what that bentonite does, or that compound does in the coffee, is you get a little bit of sodium, and it causes those, well, they're not really milk, but the, whatever it is, palm oil and, you know, whatever, those particles to disperse, and so you get that blossoming. You get the same kind of thing. Just an example, Grandma and Grandpa had soft water, water softener in the house, and I know as a kid, we had really hard water out at the farm. We go to Grandma and Grandpa's, you just kept, you couldn't feel like you were washing the soap off your hands. You felt that slick feeling. What you're seeing is a repelling force of the sodium. It's causing things to disperse. And so that's okay if you've got soft water or whatever, not so okay if you got a soil. And there are measurements we look at. In water, you'll see a sodium absorption ratio, an adjusted sodium absorption ratio. And for wastewaters, we have started to use a measurement called CROSS, calcium ratio of structural stability. And here's the calculations. And what we're trying to do is, with these measurements, we're trying to predict something in the soil. When you have a soil sample and you take a look, you may see it'll have percentage of calcium, magnesium. The number I look at is percentage of sodium, the exchangeable sodium percentage. And that is an important number when we're diagnosing these things. The higher the sodium percentage, the more sodium essentially we have in the soil, and the more dispersive that soil is. So here's an example of a sodic or high sodium soil, different effect. We go to our infiltration rate. So it's a sandy loam soil. We're applying at about 1 inch per hour. Well, we have a 1% sodium soil. After about 45 minutes, we start to see the infiltration rate drop off. We have a 2% sodium soil. After about, looks like maybe 15 to 20 minutes, it starts to drop off. Moderate, 5%, very high soil, almost immediately it drops off. And so we see the infiltration rate reaches a steady state, but as that sodium content increases, it's lower and lower and lower. And so this, in effect, we just aren't moving water in the soil at all. Now, what we do is to adjust this, when we have excess sodium, you'll hear people using gypsum. Now, gypsum is calcium sulfate, and it's a somewhat soluble salt. And we're after a soluble calcium source, okay? You could use calcium chloride or calcium nitrate. We're after the calcium. But what happens is calcium and magnesium cause soil particles to sort of clump together on those aggregates. The sodium breaks them apart. So if we have excess sodium, we've over-applied sodium to the soil, what we do is we kind of go back and over-apply soluble calcium to the soil. Calcium replaces that sodium and starts to help bring those aggregation together. So if we, in this case, this experiment, they used 5 tons of gyp, and they were able to take a very high sodium soil and take it up to the equivalent of a very low sodium soil. And so there are quality factors when we're talking about soils, taking some of these measurements. Okay, so when we look at irrigation water quality, we're looking at a primary impact. Okay, we're looking at the effect on the total salt load on crops, and we look at the sodium content on the soils. Now, there may be some other effects. We talked about the foliar injury from the chloride or boron, but there may be other effects, and you can get high iron field, you can get fouling and plugging of the screen, you can get corrosion, whatever. That's not part of this discussion. We're focused primarily on these factors. And this is a system that we use. It's diagrammed out. We use the water analysis as a predictive tool. So what we're trying to do, the conductivity, the EC of that water, soluble salts of the water, and we can measure the EC in the soil. We can take the adjusted sodium absorption ratio, and it gives us some idea of the percentage of sodium we can expect to see after, this is not like after 5 minutes of irrigation, but after a year or two or whatever of irrigation, we get kind of between the water and the soil, we get this equilibrium. So this is a diagram that or a system we've put together, and we look at electrical conductivity, and we look at sodium absorption ratio, and the conductivity, we're interested in the total salinity concerns, and the sodium, the permeability concerns. And we just have some general rankings from excellent, good, fair, acceptable, whatever. This is what gives us some idea of the irrigation water quality and some of the problems we might expect to encounter. And once we know that, there may be some things we can do to manage those problems. Now, I won't spend a lot of time here, but I put in these slides here an irrigation quality survey I did. And I looked at our irrigation samples for, it's been about 10, 12-year period. And that the cropping districts, the 3 cropping districts that would be central to your Dumas area. So looked at these measurements here, and these are the results that we found in our survey, typical results. And these are the numbers that I use as a warning. Okay, electrical conductivity, 1,500 to 3,000 micromoles. If we see a adjusted SAR on irrigation water of 4 to 7, that's a potential problem. I mean, we need to be concerned. If we have chlorides of 150 to 200, that can be a problem. And if we see boron. So those are 4 things there, and you can look at these numbers. And we have some good, we have some potential problem areas according to the survey. What I did then was I took all those irrigation water samples and by crop reporting district, and I plotted them in our system here. So we've got the northern high plains, which would catch the upper part of the panhandle, the southern high plains, southwest panhandle, and then the low plains, which is a little, probably has less irrigation in there. But for the most part, we have pretty good irrigation water quality across the board. Some problems. We have a certain number of irrigation, and these are samples that are submitted for irrigation quality analysis. I don't know for sure if they were used for irrigation or not, but anyway, that's what they told us. So we have, in all cases, fairly good quality, but we do have some problem areas. These are the ones that we need to be concerned about and we need to understand and deal with. So on this survey also, we take a look at the chloride content. And these are what I call they're called box and whisker plots. And we take all data together and stack it this way. And so this stands the midpoint. So half the samples fall below this line, half the samples are above this line. Each whisker represents 1/4 of the samples. 1/4 of the samples. And so 1/4 here and 1/4 here. So it gives you kind of an idea of what to expect. So as we look, upper plains, we have some problem areas here. We get up around this 200 mark. So we do have some potential problems with sprinkler irrigation. Now, probably has to do more with overhead sprinklers. We have our low profile sprinklers. We just simply don't put as much water on the leaves, and so that becomes less and less of a concern. But it is something to be aware of and something to look at. I might point out we have on Servitech, we have what we call our crop file. If you go to water, go to this website, Water Resource Management. We just updated this, so it's going to look a little differently. But we have some crop files, some you might say tech guides on irrigation and water quality, household water quality analysis that you can use as reference. So I'll just do a little commercial there for that. Now in that survey, I also took a look at nutrients, and we can go through this later, but looked at the per acre foot per 12 inches of irrigation. So double these numbers and you probably catch, well, depending if you're on the per 12 program, but anyway, in an acre foot, we're looking at, this is pounds of nitrogen per acre, pounds of potash, pounds, we have a lot of sulfur in irrigation water, a lot of magnesium in irrigation water. We have a fair amount of boron, not toxic at excess levels, but we also have, we pump a certain amount of lime. Now for a number of you, lime is certainly not a concern because you have alkaline soils, but we have areas where we are developing acidic soils, and this has kind of helped slow that acidity problem from developing, is our the fact that we do have a certain amount of lime in our irrigation water. Now, one of the questions I get is, are these nutrients available? Yes or no? Well, it seems to me that if I take a pint of water, raise it up to 200 feet below the land surface, pump it, go out to a spigot into a sample jar, bundle it up, and it'll spend an hour or a day or something like transit, gets to the lab, sits overnight, is analyzed the next morning, and I can still find those nutrients in there, I'd say it's going to work. So when we look at, we have water soluble and soluble nutrients. So the nitrate, sulfate, boron, they're things that can be useful in the current irrigation season. Now, we have some that are water soluble, but they're immobile in the soil, so we don't necessarily get the benefit of the nutrients this year, but they have been applied to the soil, and so theoretically they might start showing up or might next year. So take a look at an irrigation water analysis, because it can be money in the bank. Now, we certainly know with our wastewaters that we get nutrients, and this was a survey of manure samples we did, and broke this up into based on solids content. So these would be what you'd find in a lagoon. So this would be the top water in a lagoon, has very few solids in it. As we pump later, we start to a certain number of solids. And when we look at total nitrogen, we have some, and this is acre inch per acre inch. We have some nitrogen, a phosphate, and a potash. And this explains why after we start break out a field and start irrigating with wastewater, after 2 or 3 or 4 years, all of a sudden our soil test levels increase very, very rapidly, because we are pumping a large amount of nutrients. And so this is something we do have to be aware of in the long term. So urge you to get this analyzed. Now, when we look at irrigation quality rather than nutrient content, these are the irrigation quality parameters. So we do have a significant amount, potentially have a high salt content. And that's something we need to watch on these effluent irrigated fields. Take a look at our salts. Now, the sodium absorption, not so much. But I talked about cross, and with the cross, we include potassium in there. And to a degree, potassium acts somewhat like sodium. It's not as bad. But there's been some research we found that that potassium, excess potassium, can start acting like sodium, and so these cross numbers may be important. So we need to kind of keep an eye on our soils, our sodium percentages in our soil irrigation fields that are irrigated with lagoon water. We do have high chlorides, and this, depending on the crop, most of the crops that are under effluent irrigation are not going to be a problem. They're not terribly sensitive to chloride, so it's there. May not be a serious problem. One of the things I want to point out is water quality can change over time, either long term or short term. We take a look here. You hear about monitoring wells and production wells. Well, the groundwater district, Texas, they use monitoring wells, and these are observation wells looking at water depth. And they're constructed differently than what we would use. We have a little 10-foot screening at the bottom. So we're trying to get a little thin slice. We're trying to sample a little thin slice out of that whole aquifer. Now, the aquifers might be connected. They might be separated. There may be confining layers. But by putting these monitoring wells in, we can get above or below the connecting layers here. Now, production wells are a bit different, and if we look, depending on where we're located, we talk about the alluvial aquifer that may be fed by a stream, a river, or a lake or some body water. Our Ogallala water tends to be our good quality water, but below that we have what's called the Dockham and Santa Rosa, and that can be pretty nasty. But when we install production wells, very often they're screened from top to bottom because we're after yield. So when we look at water quality, we get potentially a mixture of different levels, different times, and this sort of thing. So that water quality can be rather different than what we see in a true monitoring well. And so that's important to take a look at. And I mentioned the Dockham and Santa Rosa. This is I took this out of a Texas Water Development Board report. And this is a diagram of the bedrock from Brownfield up to the Oklahoma state line, up this direction here. And there's this one from essentially Mascaro, New Mexico to Dumas, and it runs across here. And so what we see here is the Ogallala Formation overlays the Dockham, and that Dockham can be pretty thick. So we run out of irrigation water, and things can be a problem. Well, let's just drill a deeper well, and that can work against us. From that same report, here's a diagram that illustrates the sodium absorption ratio in those samples by county. And so what we're seeing here is most of the samples are represented by the blue bar, and then our extreme samples are represented by the whiskers here. And I've said here between 5 and 10 is where I start really getting concerned. Certainly between 10 and 20, that's a real, and anything above 10 gets to be a problem. So Moore County looks like we're in pretty good shape, but some of these other counties, we have some pretty significant numbers of waters that would come from the Dockham that would present us with a severe sodium problem. I have an illustration here. This was done by Tula. A consultant sent this to me a few years ago. And what the farmer did was he went ahead and he drilled a new well into the Santa Rosa Formation and irrigated the following spring with 100% Santa Rosa water, started seeing problems, so he started blending 50% Santa Rosa water with 50% Ogallala. And these bars were taken from quadrants of a pivot, so the northeast, northwest, and the southwest quadrant of the pivot. And so what we're seeing here is we started out, before we irrigated, we had a really low sodium percentage, about 1%. The first year after irrigation, it jumped up into a problem area, and then we're seeing after the second and third year of irrigation, by the time we got to the fourth year, we had a serious problem. And so these problems can develop very, very quickly. And so it's something that we have to be aware of as time goes on. So to summarize with the irrigation water quality, we talk about dissolved salts. We're talking about ions, those individual molecules, charged molecules. Some of them are beneficial nutrients. Some of them are potentially harmful components. We worry about the total salt load, the effect on the crop. We worry about the type of salt, which may provide nutrition to the crop, be a fertilizer source. It may affect the soil, maybe a bad effect. It may also affect the foliage. So to summarize this section here, irrigation water quality depends on the source. Is it groundwater or wastewater? Depends on the aquifer, the formation, well construction, how deep how the extent of the gravel pack and the screen section, where it's grouted off, and also time. And that's one of the things that can be a problem, because when we're across multiple aquifers, we can see water quality changes over time. I mentioned the deep water. We have an area in southwest Dodge City, and it's called the chloride intrusion zone. And what's happened is, over the years, some farmers, they pumped off the fresh irrigation water, and they have a deep well, and the saltier Dakota water below that has moved up. Essentially, the water level has increased because we pumped off the good quality water, and it's taken the weight off, and it's moved up. And they've had to abandon these wells because the chloride content got too high. So the only way to really know, because water can look great, and it can be a real problem. Ocean water, if you pick up a glass of ocean water, looks great, but you can't drink it. So the way to take a look at your quality is by lab analysis. Now, how often to sample? Sample every year, every third year, every fifth year, something. I think the important thing, if you have not gotten an irrigation water sample, please do so. See where you're at today, and then take one at a later date sometime. It's important to see, because this water quality can change over time, and it's important just like anything else. It's going to be too late when you see cropping problems, but if you can anticipate and see a problem developing through that water sampling. It's important. Maybe that you have to sample every year. Sometimes we see wells change between the seasons, so you almost have to take a sample after the first irrigation and during the last irrigation. And we have certain wells, depending on how they're constructed, they'll change during the irrigation cycle. So if you take it, the spring and fall, or even during the irrigation cycle, can give you two different answers.
So Fred, are you talking about sampling each pivot, or can you do per pivot?
Yes, it's really hard to, I mentioned that, I'm told this well in Tulia that I mentioned, I'm told that is not too far away from the city well, which has entirely different quality. You can have, depending on construction, you can have two wells that are side by side, and we can get two different water qualities.
So you're saying
And I'm not trying to run up the bill, but that's a fact. I've done enough water sampling that even wells that are on different corners of the corridor might depend. Sometimes there's valleys, and the topography of the aquifer below ground can be as different as above ground. Okay. Any other questions at this point? Okay. Screen sharing. Let's see if I can get that where I can see it. Well, I'm going to take this. Okay, there we go. Okay. Hopefully, what's showing up is that third portion. C is for carbon, correct?
Yes.
Yes.
Okay. Well, I want to talk about carbon, because if you haven't heard about carbon, you've had your head in the sand for quite some time. There's there's some new programs, and NRCS has been involved in it, carbon credits and that sort of thing. And there's all kinds of things there. And some of this may be old hat to you, but one of the things we talk about, organic matter or organic carbon. Okay, this is something that we hear carbon. Well, we're talking about organic matter. And when we talk about organic materials, we're really talking about, from a chemistry standpoint, carbon-containing materials. So, table sugar, cellulose, manure, diesel fuel. These are all organic compounds. Glyphosate, Roundup, is considered an organic compound because it's 21% carbon. We are about 10% carbon. And when we look at soil organic matter, about 2/3 of the soil organic matter is carbon. So we'll talk about soil carbon. If you multiply it by about 2, that gives you some idea of soil organic matter. The two would be fairly equivalent. Now here's how we measure soil organic matter. We take a gram of soil. You can see that's a pretty small amount of soil. We weigh it. We put it in a high temperature furnace. And we burn off the organic matter. And then we weigh it back, because all that's left is the mineral matter, the sand, silt, and clay. And then that's what we report on your lab report as percent soil organic matter. Now, organic matter is not just one thing. It's not little chips of charcoal or whatever in the soil. Actually, soil organic matter, going back to our earlier when we talked about the cards being clay particles, that's what you're seeing here. That's this scale. You're seeing, and I know it's kind of hard to read, but most of the organic matter, the majority of the organic matter in the soil is actually films, it's actually microbes. It's a little bit like caramel corn, if you imagine, or coating it. Take those cards and dip them in syrup and stick them together. That is actually most of the soil organic matter. Now, there is particulate organic matter that are little chunks, but on our scale, using the card as the same size as a clay particle, this particulate organic matter, this is like 2x4s, and railroad ties, and logs and such. So there is some of that, but eventually that gets broken down, the microbes work on it and reduce it, and it becomes the microbial bodies, and it becomes organic matter. So as we look at soil organic matter, there's a couple things. We have living organic matter and dead organic matter. So let's take a look here. Plant biomass, the root system, this is living and active organic matter. And this will persist for maybe days or weeks. And so as we grow crops, we accumulate biomass, we accumulate the feedstock for soil organic matter. A portion of this, several hundred pounds, is microbial biomass. Microbes, fungi, bacteria, all these earthworms and well, not earthworms, but anyway, what they do is they decompose this living organic matter, the roots and residue, and they use it for their own, they eat it, and they use it for their own life process. Well, as these microbes die, then what's left, this is dead and active organic matter. So this is kind of the equivalent of molasses or something, honey, something like that. Active organic matter. Well, that active organic matter, that does serve as a food source for the microbes, and so they kind of recycle themselves. And of course, the plants actually, the root systems do take up some of this organic matter. Well, some of this active organic matter, as the microbes work on it, it becomes more stable, okay? We talk about here, we mineralize, we convert organic matter to nitrogen, to phosphorus, or whatever to serve it. And I have longevity here. That may last months, maybe even a few years. Now, as time goes on, some of that organic matter becomes more and more stable. And this is organic matter. There's all kinds of different types of organic matter that last years or decades. And eventually the bulk of the organic matter that we have is in what we call humic materials. This is dead and inactive organic matter. This may last for decades or centuries, but this is the stuff that binds our soils together. This is the stuff that gives us our topsoil its dark color. Now, as the microbes do their thing, they're just like us. As they mineralize, as they grow, develop, they give off carbon dioxide. So eventually, some of this carbon that's in the living organic matter, it gets lost. And it gets lost as CO2. And so that's what we talk about, carbon sequestration. If we can keep the organic matter in these forms here, well then that's trapping the carbon dioxide, and it's called sequestration, the carbon. Now this is an old story here. This is from a 1950, the USDA handbook. And what they did was they tracked here in Hays, Kansas, and Wyoming, western Kansas, they tracked the decline of organic matter under cropping system. And this is what my great-grandfather, to some degree my grandfather did. They worked the ground. And as they worked the ground, what they did was they essentially burned up the organic matter, but that organic matter went on to be crop nutrients. That was the fertilizer to fertilize the wheat or corn or whatever. But it takes a toll in organic matter. So we have burned off a certain amount of that organic matter. Well, the challenge now is, if we want to restore it, here's what we do. So if we want to deplete organic matter, we remove the biomass. Okay? If you cut it off as silage rather than taking it as grain or as hay, you're going to remove more organic matter and you're going to deplete it. And you want to do things like working the ground a lot and be aerating the ground, encourage the microbes, and so they break that organic matter down. It's lost as carbon dioxide. If we want to build organic matter, we have to increase that, and in a sense, we have to limit microbial activity. That's maybe not a good way of saying it, but the less microbial activity, what it does is it preserves the organic matter that we've got. So the way it's limited here, let's take a look organic matter level across the continental U.S. And we know as we go from the west to the east, the rainfall increases. As we go from south to north, the temperature decreases. Okay, so that has an effect on biomass accumulation, the amount of stuff that is plant tissue that's available and roots that are available, and it's going to affect microbial activity. And if we look at organic matter across the U.S., as we go from west to east, it increases. As we go from south to north, it increases. So as we go from west to east, we're going from short grass prairie to tall grass prairie to forest and what have you. We're just, as the rainfall increases, we're just simply growing more stuff. As we go from south to north, the growing season gets shorter and shorter and shorter. So those microbes have less and less time to break down that organic matter. And so that's why in northern Minnesota and Wisconsin and Michigan, we have peat bogs. It's cold enough that we accumulate organic matter in those situations, and it just simply doesn't get broken. Now, the precipitation, temperature is important, but annual precip is only one consideration. And I've picked some locations here. Amarillo, our annual rainfall is about 20 inches. Bismarck, North Dakota is about 18 inches. That's actually Gabe Brown, his farms near there. Des Moines, Iowa. Bloomington, Illinois, if you follow Ken Ferry, that's where he lives. And of course, where our beloved congressmen live here in Washington, D.C. So these are what shows up in the gauges is one thing, but it's really important to take a look at evaporation. This is a map of lake evaporation, open pan of evaporation, inches per year. In the panhandle, we potentially lose 90 to 100 inches through the year by evaporation. Now, that's offset by rainfall, but we do potentially dry out. And as we move north and east, that open pan evaporation drops off, becomes less and less. And so that's going to have an impact. So what I did was I took those same locations and I took open pan evaporation and divided it by the annual rainfall. And in Amarillo, we have about 5 inches of evaporation to each inch of annual rainfall. Now, we go to Bismarck, roughly the same annual rainfall, but now we're at 2.5 to 1. We go to Bloomington, it's almost 1 to 1, which is why they have rivers and streams, because the evaporation is significantly lower and closer to the annual precipitation. In fact, this line here is where precipitation and evapotranspiration are approximately equal. So here it's drier, here it gets wetter. So if we want to build soil organic matter, so let's borrow this idea here. If I've got a soil with 1% organic matter with 6 inches, I've got about 20,000 pounds of actual organic matter. Now, over a year's time, just under normal conditions, I lose about 1%, so roughly 200 pounds per acre, and that's from that carbon dioxide loss from the normal function of microbes. All right, I want to raise it by 1/10 of 1%, so I got to add 2,000 pounds of organic matter. So here I go, I grow, and this works out 2,700 pounds of annual biomass, and it's roughly half grain and half residue. That's a pretty standard. So that would be about 240 bushel of corn and about 235 bushel of wheat, if you're able to do that. So we harvest, and so that organic matter is gone, that biomass is gone, but this gets returned to the soil. Now, over time, long term, only about 10% of that actually shows up as measurable organic matter. Over time, the other 90% is lost by respiration. So not all the residue we put on this year, only about 10% of it is actually long-term going to enter into the soil organically. Now let's add cover crops, so we're adding more organic matter. So we do add biomass, and even though it's 10%, we still increase the amount of biomass that's available to become organic. So this is an ongoing cycle, and becomes really important. Now, this is a study that was actually done in 1910 and 11 to kind of put this all together. And what they did was the scientists went at that time and how much water it took to grow alfalfa. And this is pounds of water to produce 1 pound of alfalfa dry matter. Okay, 1,000 pounds of Dalhart, and up in North Dakota, only about 500 pounds. Just like that map I showed you earlier, essentially what they're saying here is an inch of rainfall here in Dalhart only goes about half as far as it does in North Dakota, and that's because of the evaporation. So it's important to look behind the scenes and not just at total rainfall. Now, I took the math here and did some math using this assumptions here. We're talking about annual precipitation, used the numbers from that 1910 study and figured out how many gallons per acre that would receive each year and how many tons of alfalfa it would grow. So up in Williston, 3.5 tons, Delhart about 2 tons based on these research. And if only 10% of that wound up as soil organic matter, essentially we're looking at twice as much annual organic matter being built up as in North Dakota as Delhart. But it's also a very small amount. We would expect about 0.1% of organic, or 0.2%, 0.02% per acre per year to increase using these numbers. So how does that play out in real life? Again, going back across the reports, he has 20 years, he's taken his organic matter from about 2% to 6%. There's another time from about 2% to 11%. So that's pretty significant. That's pretty impressive. So I wanted to take a look at, do we have research that would carry that out? Well, here's a study that was done at La Mesa, Texas, and this is really low soil organic matter. It was cotton, and they used rye as a cover crop. Anyway, it's about 1/3% of organic matter, sandy soil and whatever. Well, they doubled their soil organic matter over a period of time, over 19 years or whatever. Anyway, I did the math, and I won't spend a lot of time here, but I estimated that rye cover crop produced about 2 tons of dry matter. And if I ran through some of the math, and you can go through this here, but I would expect, based on some of these this other information I had, that we're going to see about 0.016% increase in soil organic matter per year. So about not quite 0.02% per year. Well, that seems low. But then I took the 19 years of the study and I doubled that. By doubling that, I came up with 0.3% organic matter increase, which is about what they said. So I felt my numbers were pretty good, my assumptions were pretty good. So I started looking around a bit, and I looked at Tribune, Kansas. And this is a study that's been going on for the last 60 years. Continuous corn and sorghum irrigated, different rates, and started out with soil organic matter 1.4%. And this graph I'm showing you, they had different nitrogen rates from 0 to 200 pounds of nitrogen every year since, whatever it was, 1968, and no phosphate. So as we look, this top, the brown line is sorghum, the green line is corn, the organic matter in those plots. They measured them in, this is in 2020. So with sorghum, without any fertilizer, just increase your organic matter by 0.5%. When we added 200 pounds of nitrogen over time, we increased it by 0.9%. This is conventional tillage. This is nothing special. If we looked at the corn, we increased it by 0.3 and by 0.6. So as I look at this, kind of what this tells me, since there was no fertilizer applied, this 0.3 and 0.5, that organic matter increase was due to improved genetics and irrigation. We were able to just increase the yield with those two things over time. Increase the yield, so increased not only grain yield, but increased biomass, and eventually that was reflected in organic matter increase. Now, when we had 40 pounds of phosphate, 40 pounds of phosphate, now our nitrogen rate, even low nitrogen, with the sorghum, we popped that up by 0.9. We reached our peak organic matter. And corn, we reached 0.7. So when we fertilize, not only did we improve the crop yield, but we also probably helped develop more biomass. So even under these conditions, we were able to increase. So what I did was ran the math here, doing these comparisons. But anyway, the increase at Tribune was 13 thousandths of a percent organic matter per year. And I compared that to La Mesa, and it's surprisingly close. But they're in somewhat similar climate. I ran across this study from Iowa. There's 4 locations, continuous corn and corn soy rotation. And they were trying to look at nitrogen rates, what it did in terms of organic matter. And welcome to Iowa, about 3.5 to 5% organic matter. So can we increase organic matter there? Well, yes we can. And here's what they compared. Now, they averaged, because there were different locations and stuff, the nitrogen rates and the change in soil organic matter or organic carbon is this. So the dashed line is even. If we see the rate above the dashed line, we're gaining organic matter. If it's below the line, we're losing organic matter. And they looked at optimum nitrogen rate. So 100% is the optimum nitrogen rate. With continuous corn, we increased organic matter over the period of the study. With soybeans, slowly, but not much. We really didn't increase organic matter with the corn soy rotation. And part of that is just due to the fact that the corn residue is more resistant, doesn't break down. The soybean residue does. So with the soybean residue, we had less stuff out here. Plus we had residue that broke down more rapidly. And this is what it looked like with no nitrogen, agronomic, the optimum rate, right where we reached our peak. And the optimum rate, if we applied nitrogen beyond that, we really did not increase the yield. In fact, we can get excessive. So here's what happened to the crop biomass. It increased, leveled off. Carryover nitrate, once we got past that optimum rate, started to increase. So we had a lot of carryover nitrate here. In fact, what it did in terms of organic matter accumulation was it may even have caused a drop off in accumulation. What you did with that extra nitrate, it stimulated the microbes, and so they worked a little longer and actually tended to break down the organic matter. I've heard there's people that say nitrogen burns up organic matter. Well, excess nitrogen burns up organic matter. Optimum nitrogen builds organic matter. So take a look, and these are the numbers I ran. Take a look, ignore all this, but down here, across the board, we averaged 9 1/1000ths of an increase, percent increase in that soil organic matter each year. And we start comparing that. I compare Iowa to western Kansas to western Texas, and they're surprisingly similar. I was very surprised by that. I took a look at, this is one of our agronomists in south central Kansas, south central Nebraska, and he sent me 30 years worth of, he's been at it, he's a gray here, but he's been at it, and these are the organic matter results he sent me for 3 different fields. And what I did was I tried to figure out what kind of organic matter increase we had. Well, in this case, we didn't have much change. In this case, we didn't have much change. Now, here we had some increase by 7 1/1000ths of a percent per year. And when I stack them all together, I look at south central Nebraska, Iowa, western Kansas, and southwest Texas. And actually the numbers are surprisingly close, considering the great difference. Now when I look at what Gabe Brown, going from 1.7 to produced, that's almost a 0.5% change in soil organic matter each year. And if I was using rye to increase that organic matter, run through the math, I'd have to have close to 200 tons of rye silage per acre per year to meet that. So I don't know there's no more information about how he did this, he claimed as his rotation or whatever, but I just find that there's a big disparity between what I see in controlled long-term research and what we see here. So I think there's some answers there, but I'm not sure. We've got to ask the right questions, I guess. So I want to kind of wrap it up here. Not all organic matter is equal. There's living organic matter and dead organic matter. Some of it's active, some of it serves as a food source, some of it is inactive, which helps stabilize the soil. it takes time to make measurable increases, okay? Now, this is an important consideration. We can see those changes occur very, very quickly in the top couple of inches. So we can build organic matter really rapidly. Now, building it to a depth of 6 inches or 12 inches, that's a different story. Now, this organic matter that we build quickly, you can think of that active organic matter. I call it easy come, easy go. It's not very durable. If we think back to that diagram talked about, showed the stepwise organic matter, you can almost think of like at the top, we've got things like molasses and honey, and then we've got paper and that sort of thing, and then the next organic matter would be like wood, like pine, and even hardwood like oak and maple. And that humid materials, that's almost like asphalt, very, very durable. So we have a lot of difference in those organic matter sources. Well, we can build that that active organic matter fairly quickly, but by the same token, if we start, make a management change, it can go quickly. So thinking about terms of building soil organic matter, it may take years, it may even take decades before we can see important measurements. So I think that a realistic increase in soil organic matter under, we'll say, normal management, typical management, super exceptional, we look at 10 to 15 1,000% per year. So we're looking at about 0.1 to 0.5 increase in soil organic matter after about 10 years. And I do think that's realistic. And I bring that up because I think I read about rapid increase in organic matter. I think this is realistic, and I think this is practical. Just create some expectation. Now, anytime we want to increase organic matter, we have to increase biomass somehow. We've got to conserve resistant residue. So corn residue is more resistant than other residues. So anything we can do to kind of preserve that. We increase yields, more grain, more stalk, more leaf, or whatever, so more biomass. So that's it. And we use optimum, but not excessive nitrogen rates. So this all plays into our overall management system. Now I'm going to wrap it up here in this session with the soil health checkup. A fellow by the name of Andrew McGuire at Washington State put this ladder together. I really like it because I know there's a new NRCS program out where they're testing for soil health. I don't know, I don't know the details, I just know that it's fairly recent. But anyway, these are some questions that you can ask, okay? And a yes or no answer. Does the soil blow or flow away? If it's yes, probably not healthy. If it's no, probably healthy. So we can step through there. So the first three there of this, we have good infiltration, we have good internal drainage. That's something you can see from a day-to-day basis. Now, does the soil crust or seal up? That's where we need to maybe check the soil test, check the sodium. We need to check the SR, the irrigation water quality, if we're starting to see problems. Does the crop recover the nutrients? Well, that's just a soil test history. Can we see trends? Do we see our soil test increase, decrease, or stay the same? Now, plant tissue analysis helps with all that. And then are there areas where plants die or grow poorly? I found that if it's not due to some compaction or disease or whatever, if we look at soil pH and soluble salts, that is a very, very common problem where we see plant growth, poor growth, or even plant death. So these are some things that, just a quick way of evaluating soil health, and you can do it with stuff you've already got in place. And the last slide here, this is an interesting slide. What this is a way of, presented as a way of measuring microbial activity. Okay, so we have cloth, which is cellulose, and it's an organic compound. So you take a pair of nice new clean undershorts, not used, new ones, and you bury them in the soil, and then you dig them up after a period of time. And so the degree of decomposition tells you something about the microbial activity. The more ragged those underwear are, the more microbial activity you have. So that's what this is supposed to represent. I've had somebody tell me, said, well, you know what this looks like? This looks like 4 farmers, and it's about 5 minutes after they got done renewing their annual operating note, and their loan officer has expressed his concerns with them, and that's what their shorts look like. So, be it as it will. So, anyway, that's it. Just, oops, here we go. Still speaking? Okay, Mike.
Okay, have questions for Brett? Grow a cover crop, how long is it gonna take to add 1% organic matter? Brett?
Excuse me?
You grow cover crops, how long is it gonna take you to add 1% organic matter to the soil?
1%?
Sure.
Take a look
In the
at
high plains.
In the high
In
plains.
Dumas.
I think that number, if we take a look and you can do some calculation, look at the percentage of dry matter, and not wet but dry matter, and 10% of what the extra that you apply ultimately might wind up. So without doing the math, it would take a lot. It would take let's use the La Mesa study for example. That was about 4,000 pounds of dry matter a year as rye cover crop. So multiply that by, we saw 10, so multiply that about 6. So you'd have to have about, let's say 12,000 pounds. I'm working this in my head. 12,000 pounds of dry matter too. Now that would increase it by a 10 over a year's time. So you'd have to have a lot more to do that in 1 year. It's a slow process. Now, I will point out sampling depth is important. If you're talking about the top inch or 2, that's a different story than if we're talking about 6 inches or 12 inches. So without punching a calculator, I'm just going to say it would take a lot.
How about no-till?
Well, no-till is
Conventional.
kind of interesting because no-till, the residue that you see laying on top, when we analyze a soil sample, that is a very, very small amount of the total organic matter. In fact, that residue, if it's laying on the soil surface, it's not part of the organic matter. Microbes can't work at it. And it isn't until the microbes actually get on it that it eventually becomes organic matter. And people worry about sending in a sample with pieces of stalk or whatever. In our that's all gone. Now, one of the things that no-till would do is by not tearing up those root channels, you're going to increase the infiltration rate. And ultimately, so that means you can have better subsoil moisture storage, and so you're just creating a better environment for the microbes, for them to work and to break down the residue into the permanent soil organic matter. Residue is very, very temporary organic matter, but we're looking at permanent organic